The paper presents an adaptive, autonomous system for surface crack detection and repair using robotics with advanced sensing technologies. It utilizes an RGB-D camera for crack detection, a laser scanner for precise measurement, and an extruder and pump for material deposition. A novel validation procedure with 3D printed crack specimens simulates real-world cracks and ensures testing repeatability. The study demonstrates that an adaptive system for crack filling is more efficient and effective than a fixed-speed approach, with experimental results confirming precision and consistency. This research paves the way for versatile, reliable robotic infrastructure maintenance. The introduction highlights the importance of efficient detection and repair of surface cracks in infrastructure maintenance, as they can lead to long-term deterioration and costly repairs if left unchecked. It also mentions the economic impact of such repairs, such as flight cancellations and delays at San Francisco International Airport. The paper then discusses recent advancements in crack detection, sensing, and measurement, including the development of datasets for deep learning, unmanned aerial vehicles, UAVs, data acquisition, application of deep networks for damage identification, and visualization for decision-making. The paper also covers advancements in robotics technology for enhancing the efficiency and precision of manual repair tasks in various infrastructure maintenance. Researchers have developed semi-autonomous vision-guided systems for crack filling and designed robotic arms capable of precise crack repair. The paper concludes by emphasizing the potential of integrating advanced sensors, image processing, and data fusion techniques to enhance precision and efficiency in crack detection technologies, as well as leveraging robotics technology to improve the efficiency and precision of manual repair tasks in infrastructure maintenance. Autonomous crack repair systems have demonstrated promise in adapting to various crack conditions, with advancements in visual data tracking, path planning, and end effector designs. However, challenges persist in integrating detection and repair functionalities, particularly in real-world testing and validation. This paper proposes a novel methodology for crack repair, addressing both detection and repair with high precision. The methodology consists of 4 parts: extrusion calibration, crack coordinates extraction, crack profile measurement, and crack filling. The system integrates a robotic arm and custom end effector, combining RGB-D camera and laser scanner data for precision measurements. The calibration process determines the extrusion rate at different speeds, ensuring reliable material deposition. A laser scanner provides 2D measurements, and a heuristic algorithm is employed to calculate the actual width and height of the print. The crack coordinates are extracted using an image to segment the crack, and refined with the laser scanner to enhance precision. The crack filling process involves pumping material from a custom-designed, 3D printed pump to the print head, extruded at a constant flow rate driven by a microprocessor. The robot moves to the coordinates at assigned speeds to ensure precise filling. The proposed validation methodology involves rescanning post-fill profiles, applying heuristic algorithms to detect cross-sectional area, and ensuring the crack is properly repaired. The system is tested in both simulation and laboratory environments, demonstrating the effectiveness of the adaptive crack filling system. The contributions of this research include an autonomous and adaptive crack filling system, a novel computer vision pipeline, and a repeatable validation procedure using a 3D printed crack. The system addresses the challenges of integrating detection and repair functionalities, providing a comprehensive, end-to-end, adaptive, and autonomous solution for crack repair. The research paper presents a crack detection and coordinate extraction method for robotic repair systems. The method begins with the calibration of the laser scanner data, where the sudden change in laser depth Z is used to determine the cross-sectional area and center position of the crack. This is represented by equations 3 and 4, where I1 and I2 are the indices with the largest sudden change in laser depth. X1 and X2 are the X values from the laser scanner data. A is the cross-sectional area. Delta X is the change between the X values, and CK is the center position of the crack in the axis. The crack coordinates are then extracted by detecting cracks using a segmentation model applied to RGB images, followed by extracting centerline pixel coordinates through skeletonization. The detected pixels are transformed from camera coordinates to robot coordinates using the pinhole camera model, and the final path is optimized using a heuristic approach. The crack detection process involves feeding the captured RGB image into a pre-trained Deep Lab V3+ model, which segments the crack and outputs a black and white image mask highlighting the crack. The segmented mask is then converted to grayscale, followed by binary thresholding and skeletonization to extract the pixel coordinates of the crack. The skeletonization operation reduces the crack representation to its thinnest form while preserving the overall structure. The pixel coordinates are then transformed into 3D camera coordinates using the pinhole camera model, which translates the 2D image data captured by the RGB-D camera into a spatial format that the robot can use. The intrinsic camera parameters, including the focal lengths and optical center, are encapsulated in the K-matrix, as shown in equation 5. The transformation from pixel coordinates to camera coordinates is illustrated by equation 6, where the camera coordinates represent the 3D points in the camera's coordinate system. K is the intrinsic matrix, and pixel coordinates, U, V, are the 2D points from the segmented image, with ZC being the respective depth values obtained from the RGB-D camera. The proposed method enables accurate and efficient crack detection and coordinate extraction, forming the basis for the subsequent stages of the repair process. The use of a robust crack detection system, advanced image processing techniques, and precise camera modeling ensures that the robotic system can accurately navigate and repair cracks in various structures. The research paper discusses the development of a robotic system for crack repair in concrete structures. It begins by describing the pinhole camera model and its transformation from camera coordinates to robot coordinates. The process involves converting pixel coordinates to robot base coordinates using the camera's extrinsic parameters and the robot's API. This transformation is crucial for the robotic system to interpret and act upon the spatial positioning of cracks accurately. The paper also presents a heuristic approach for path optimization, aiming to minimize travel distance and ensure complete coverage while avoiding redundant movements. The algorithm sorts the robot coordinates based on the maximum distances between the X and Y coordinates, ensuring efficient navigation along the crack. While more advanced algorithms might be necessary for complex patterns, the heuristic approach proved sufficient for the tested crack patterns, enhancing the robot's efficiency and precision. The research paper discusses an innovative method for detecting and repairing cracks in concrete structures using a robotic system. It utilizes a combination of RGB-D camera and laser scanner to accurately identify cracks, and a robotic arm to fill them with a specialized material. The paper outlines the process of enhancing the initial crack coordinates detected by the RGB-D camera through laser scanning, which provides high-resolution data along the crack. This data is then used to generate detailed 2D profiles at regular intervals, allowing for precise material deposition during the repair process. The transformation from laser coordinates to robot coordinates is achieved using a transformation matrix derived from the laser scanner's translation and rotation parameters. This ensures that the robot can accurately navigate to the crack coordinates and deposit the filling material accordingly. The robot's speed is adjusted based on the cross-sectional area of each crack coordinate, ensuring efficient and effective filling. A validation process is conducted after the crack filling process, where the laser scanner performs a post-fill scan to assess the effectiveness of the repair. The absolute normalized difference between pre-fill and post-fill profiles is calculated to quantify the accuracy of the repair, with a lower value indicating a more accurate and effective repair. The paper also describes the simulation and experimental setup used to evaluate the performance and validate the functionality of the automated crack repair system. RoboDK, a robust robot Python programming API, is chosen for its cost-effectiveness and ease of integration with real robots. The simulation environment allows for testing and refining the system in a controlled virtual setting before real-world deployment, ensuring that potential issues are minimized and performance is optimized. The experimental setup involves the physical implementation of the automated crack repair system, focusing on the system design and the end effector's functionality. The system design integrates various components, including the universal robot's UR10E robotic arm, end effector, pump, microprocessor, and 3D printed crack specimen. The UR10E robotic arm navigates along the crack, performing the repair with precision and versatility. The end effector, consisting of an Intel RealSense D435 RGB-D camera, micro epsilon scan controlled 3002 laser scanner, and a printhead, is crucial for material extrusion. The RGB-D camera captures images of the crack, while the laser scanner enhances robot coordinates and creates detailed crack profiles. The printhead manages the material flow, ensuring consistent extrusion. The system's design facilitates efficient and accurate crack repair, demonstrating its potential in real-world applications. The automated crack repair system is a complex process that requires precise calibration and validation to ensure optimal material flow during repairs. This system consists of a robotic arm, a pump, and a 3D-printed crack and filling material. The pump design is influenced by the structure of a medical syringe, featuring a cylinder-to-cone shape and a plunger mechanism that facilitates the extrusion of material from the pump to the hose and ultimately to the printhead. The efficiency of the pump is influenced by the diameter of the barbed hose and the viscosity of the material. Several modifications were made to improve the pump's performance, including increasing the infill of the 3D printed pump for enhanced structural integrity, minimizing tolerances for the O-rings to prevent leakage, adjusting the design to handle different viscosities and types of materials, refining the design for safety and ease of use, and minimizing material waste and enhancing the overall efficiency of the extrusion process. To test and validate the automated crack repair system, 3D-printed crack specimens were created to mimic real-world crack patterns. These specimens represent various crack widths, depths, and orientations, providing a robust testing environment for the repair process. Play-Doh mixed with water is used as the filling material due to its ease of testing and reusability. This mixture can be replaced with other materials by repeating the calibration setup. The 3D-printed crack specimens are then placed in the testing area, where the robotic system applies the filling material according to the programmed repair procedure. The calibration results demonstrate the relationship between the robot's speed and the amount of material extruded. Various speeds were tested, and the cross-sectional areas of the extruded material were measured. The results show a clear inverse relationship between the robot's speed and the material extrusion rate. As the robot's speed increases, the amount of material extruded decreases, and vice versa. This calibration allows for associating specific speeds with their corresponding cross-sectional areas, which is essential for the crack filling process. Each crack coordinate, having varying sizes, requires an appropriate speed for optimal material extrusion. The validation results assess the accuracy of the crack filling process, comparing pre-fill and post-fill profiles to evaluate the system's effectiveness. A video link demonstrating the whole crack filling process can be found here. The paper presents a novel design for an adaptive, autonomous system for surface crack detection and repair using a robotic arm equipped with advanced sensing technologies. This system integrates an RGB-D camera for initial crack detection, a laser scanner for precise measurement and profile generation, and an extruder for material deposition. To enhance repair precision and efficiency, the approach first automatically calibrates the relationship between the robot's speed and material extrusion rate. Then, the system utilizes precise crack perception to ensure optimal material flow for varying crack sizes. A novel and repeatable validation approach using a 3D printed crack was developed to evaluate the performance of the proposed system. The experimental results demonstrated the system's capability to perform crack repairs effectively, balancing the trade-off between repair time and filling precision. The use of 3D printed crack specimens and a specially formulated filling material provided a robust and repeatable testing environment, closely simulating real-world conditions. The post-fill validation process, involving laser scanning and fill error calculation, highlighted the system's effectiveness in achieving accurate repairs. Table 2 shows the error values epsilon fill for various constant speeds, including adaptive speed control. The results indicate that adaptive speed control achieved the lowest error or highest accuracy, with a mean epsilon fill of 0.305, a standard deviation of 0.240, and a median of 0.265. In comparison, fixed speeds of 6 mm per second, 8 mm per second, 10 mm per second, 15 mm per second, and 20 mm per second resulted in higher mean and standard deviation values, pointing out less precise filling with a higher degree of overfill or underfill. Figures 12 and 13 demonstrate the qualitative performance of different robot speeds during crack filling, where the adaptive speed shows the least amount of overfill and underfill. The repair process time also varied with speed, with adaptive speed control completing the process in 24.784 seconds, compared to 39.844 seconds for the 6 mm per second speed and 19.102 seconds for the 20 mm per second speed. While the 20 mm per second speed resulted in the shortest repair time, it bargained the filling accuracy, leading to higher deviations in the filled profiles. On the other hand, the adaptive speed control not only provided the most accurate filling but also optimized the repair time by balancing speed and precision. This research highlights the potential for adaptive, autonomous systems to significantly improve the quality and efficiency of infrastructure repair maintenance. Autonomous crack repair has the potential for widespread adoption across various infrastructure sectors, ranging from residential, commercial, and transportation infrastructure, leading to enhanced safety, reduced maintenance costs, and extended lifespan of critical structures. By minimizing the need for manual labor, this approach not only improves worker safety but also meets the growing demand for automated solutions in infrastructure repair and maintenance. The authors declare no competing financial interests or personal relationships that could have influenced the work presented in this paper. Data will be made available upon request. The authors acknowledge partial financial support from the Department of Defense and express gratitude for the use of the Cabrera cluster and advanced support from the Research Computing Data Core at the University of Houston. The paper cites various references related to post-earthquake building assessment, 3D printing technologies, and computer vision-based civil infrastructure inspection and monitoring. The authors also acknowledge the use of ChatGPT to improve readability and language, with full responsibility taken for the content of the publication. The references provided discuss various topics, including automatic crack detection and 3D reconstruction using underwater wall climbing robots, robotated tunnel inspection and maintenance systems, and self-reconfigurable facade cleaning robots equipped with deep learning-based crack detection. Other references explore vision-based integrated mobile robotic systems, intelligent robotic systems for structural health monitoring, and multitask semantic segmentation of multiple types of structural materials and damage in images of civil infrastructure. Additionally, the references cover fusion of thermal and RGB images for automated deep learning-based crack detection, dual-path networks combining CNN and transformer for pavement crack segmentation, and AI and robotics-assisted automated pavement crack evaluation systems. Other topics include motion planning and control of automated crack-filling robots, multi-scale robotic approaches for precise crack measurement, and 3D vision technologies for structural external crack damage recognition robots. The authors provide a comprehensive review of existing research in the field, highlighting the significance of computer vision, machine learning, and robotics in civil infrastructure inspection and maintenance. The references demonstrate the potential of these technologies in improving the efficiency and accuracy of crack detection, assessment, and repair in various infrastructure applications. The research paper discusses various aspects of semi-automatic crack width measurement, autonomous robot systems for pavement crack inspection, and advanced algorithms for crack detection. The ortho-boundary algorithm is introduced for semi-automatic crack width measurement. Autonomous robot systems are designed for crack inspection, utilizing CNN models for efficient detection. The paper also highlights advanced algorithms for crack detection, including feature pyramid and hierarchical boosting networks. Additionally, it discusses the use of robotic arms for semi-autonomous concrete crack repair and the development of climbing robots for repairing cables of cable-stayed bridges. The summary covers the design and implementation of manipulator systems for roadway crack sealing, complete and near-optimal path planning for simultaneous sensor-based inspection and footprint coverage, and the integration of aerial soft continuum manipulators for predictive maintenance. It also touches on the use of machine learning for crack detection and the development of extendable open-source structural inspection datasets.